Good afternoon. My name is Jane Hayes, and on behalf of my co-authors, it's an honor to be here at the AIR workshop to present our paper. Our colleagues in the area of campus network security note a lack of specification, in natural language text, of the security requirements and security policies for these networks. The community has thus been working to document their policies. If you examine this domain, you'll see that these universities have an online system, which is their campus network and its services, and they have a need for security requirements. They basically have a requirements problem, a need to specify the requirements and then ensure that those requirements are being satisfied. Our goal is to help improve the quality of campus network security. The universities strive to have a hierarchy of these documents, acceptable use policy at the high level, and then college level policies, departmental policies, then very low level network rules that will fire and result in logs. In many cases, the only document we were able to find in common across universities was an acceptable use policy, or AUP. Our goal is to help universities write better security requirements in AUPs, so we need to discover the topics that should be in an AUP in an automated fashion, then check the completeness of a given university's acceptable use policy. Thus, the idea of domain-specific completeness analysis and our interest in using AI for topic modeling. We had two questions. Can we come up with the de facto set of topics that constitutes a complete campus AUP? And can we determine automatically whether a particular topic was covered in a given AUP? We thus undertook a feasibility study to see if an automated unsupervised topic modeling technique, latent Dirichlet allocation, or LDA, could help us identify topics in these network security policies and predict the presence or absence of those topics. LDA analyzes textual documents and assumes that every unit of text of a given granularity, sentence, paragraph, section, was put there to address a specific latent topic. Given a specific number of topics, the LDA method assigns each unit of text to a specific latent topic. It produces a vector of topic weights or loadings, where each weight indicates the proportion of the document devoted to a given topic. Additionally, LDA associates with each latent topic a separate probability distribution over the words found in the document. This allows us to conveniently represent latent topics using the most probable words for each of them. This, in turn, means that some, although not necessarily all, latent topics can be interpreted by human analysts as carrying specific semantics. We started by creating a collection of campus AUPs. The AUPs were parsed and run through LDA. We examined the topics produced by LDA and found there meaningful themes and converted them into actual network security policy topics. We looked at the topic loadings returned by LDA for each AUP, and higher topic loading values indicate that a topic was substantially covered in a document, and vice versa. We took a sample of the AUP documents and asked experts how well each topic learned with LDA was represented, thus testing our predictions. To see how well LDA identified the absence or presence of specific topics, we compared it to two baseline methods. The frequency count method looked at the top 25 words LDA had associated with each topic. In a nutshell, where the normalized frequency of the words representing the topic was 25% below the mean, we considered that insufficient coverage of the topic. We also used the section headings method. This method extracts the words found in the headings and checks whether or not those words match any of the top 25 words for a topic. A matched term results in predicting that the topic is sufficiently represented. To extract topics, we started with over 200 AUP documents from websites of different United States universities. We collected them in PDF and then converted them into plain text. A few problematic files were excluded, so we ended up with 231 documents. They ranged in size from 1 to 2 pages to 15 to 20 pages. We ran LDA a number of times to calibrate the number of topics and then examined the list manually to see if we agreed with the most relevant words and to see whether or not we could name the topics. After that, we picked a winning LDA run and it had 20 latent topics. Some of them, unfortunately, were junk topics. The remaining 11 topics are shown here on the slide, along with some of their indicator terms. You can see that there are clearly identifiable topics: appropriate use of resources, network access, etc. These are meaningful topics for campus network security. Also, the keywords indicate that they're fairly distinct. In order to evaluate our work, we used student review and treated them as experts and also as ground truth yielding. These 25 students were taking an undergraduate wireless security course at Cal Poly. We had 23 policy documents that we randomly selected from the 231 that they read and evaluated. We asked them to indicate for each of the 11 topics the level of coverage as either being absent, insufficient, sufficient, or overrepresented. Absent and insufficient were equal to insufficiently covered, and sufficient and overrepresented indicated that a topic was sufficiently covered. We used the typical measures of recall, precision, and F1, and viewed positive recall, precision, F1 as the measures for the sufficiently present prediction, and negative recall, precision, and F1 as the measures for insufficiently present prediction. We're mostly interested in topics that were missed in a policy, so we chose sufficient-insufficient threshold to be the most favorable for us. We thus optimized the negative measures. Next, we look at the results. The 11 topics were all confirmed by LDA and the human experts, and these same topics all also appeared in the literature, as we did an independent literature survey. We didn't uncover any topics of significance that were missed from our list. We next examined the accuracy of LDA. This table shows the accuracy of all 3 methods for each of the 11 topics. The frequency count method outperformed LDA on 2 topics, and the section heading method also beat LDA on 2 topics and tied it on 2 topics. LDA tied or beat the baseline methods on all but 2 topics, shown here. So overall, LDA outperformed these methods. In summary, we did find some interesting results and were able to apply LDA for topic modeling to this domain of network security requirements. We applied some ideas from the requirements engineering world in terms of evaluating completeness for these network security requirements and AUPs. There were a number of limitations we hope to address when we do a more in-depth analysis of our proposed approach. For example, we'd like to analyze an unseen network policy and then correctly predict what topics are insufficiently covered in it. Finally, we'd like to thank the NSF for partially funding this work, and we'd like to thank the Cal Poly students for undertaking this study, and also Dr. Ting Ting Yu for helpful discussions on experimental design. Thank you.